Welcome back to ECE 442-542. Homework number 7, as a reminder, is due a week from Friday on the 1st of May. We're running out of days. Your project for 542 is due 2 weeks from today. Is that right? I believe it is. The 6th. And teacher course evaluations are due on the same day. And there's the link if you haven't received the email. I'm assuming you have received the email or emails if you haven't yet filled that out, and it is good to hear from you. I didn't check today to see the number of students that have participated yet, but maybe I'll do that next time. Maybe once a week I'll check that and see how we're doing for participation. Final exam again is on a Thursday, the 14th of May, and it's much earlier in the day. It's from 1 to 3. Today what I want to do is start with PID control, really show you what that looks like generically. By generically, I mean that could be either analog or digital, and then we'll simply show you the analog piece. It's cleaner maybe or easier to think in analog terms or in the S domain when we speak of proportional, integral, and derivative terms. We'll look at the structure, then we'll just show you what it looks like in the discrete time sense or for a difference equation, and then we'll derive where that comes from. But I'll quickly scroll through that, and we'll spend more time on the examples of how do we really place the two zeros that are now available to us in the PID controller design. That's what we will end up having the flexibility to do, is placing two zeros if we use all three terms, the proportional, integral, and derivative term, in the PID controller. Then if we have time, we will start what I will describe as a generic controller design. And by that, now we do have our shakers. We have our zero shaker and our pole shaker, and we can liberally sprinkle those, or we may not want to get too aggressive. We don't want to put too many poles or too many zeros. But to have a to have a causal controller, it might be casual, but causal, what do we need relative to the poles and zeros in our controller? A relationship. Do you remember what that means? Pardon? So we want, in terms of orders of polynomials on the numerator and denominator, for it to be causal. So right-sided, it would be a signal. But if we were thinking in terms of a transfer function for a controller, then we need the orders of the numerator and denominator to at least be equal, and the denominator order could be greater than or equal to the numerator order. And that's when we're speaking about a system and not a signal. So yes, it depends on what we're speaking of when we say causal in terms of behavior or description. Let's start to scroll through this development of the PID controller. The block diagram really hasn't changed. It's just now in our controller block, we're introducing one more piece, a derivative piece. What did the integral piece allow us to do? Do you remember what that provides for us in terms of system behavior? Pardon? So the integrator is using past error information, isn't it? And we're integrating that up, and that allows us actually to improve our steady state accuracy. So we're using previous information from our error signal to actually produce a better steady state accuracy. Let's say we put in a 10, we want to go to 10, we might want to introduce an integrator if one doesn't already exist in our system in the forward block. And now we're assuming this negative unity output feedback configuration. The derivative piece does really just the other side of the coin. We need to worry about steady state accuracy, and we need to worry about transient performance. And the derivative allows us to potentially improve the transient performance of our closed loop system. And it anticipates what might happen in the future with our error signal. That derivative gives us sort of the slope information at the present time. The P just operates on the error signal right now. And there's the structure, the PID structure. K sub P, integral is K sub I over S, if we're thinking in terms of the transform description of these operators, and the derivative is simply K sub ds. Then we can factor out the K sub P. We can write this controller in many different ways, and I'm doing that so that you get comfortable. If you see this in another source or in a paper or a textbook, they might represent this PID controller other than just the K sub P, K sub I, and K sub D. If you factor out the gain that's common to all three, now you sort of take this ratio with K sub I and K sub D, you're factoring out the K sub P. But in the third form of this controller, we are now using that gain that's scaling an S in the numerator or in the denominator. We're really rewriting that gain to be a constant in front of S. And what are the units on S? What is S? It's a complex frequency variable, isn't it? So it's per second, radians per second, let's say, and radians is dimensionless. We now have T times per second. What is T? Unit-wise. It's in seconds. It's in units of time. So these T sub I, that's our integral time, and T sub D, which also scales S, is our derivative time. You might see people referring to these PID controllers in terms of the overall gain K and a integral time and a derivative time, but those are just ways of scaling the integral term in the controller and the derivative term. These are all just different ways of representing the same controller, a PID controller. And that's what I'm trying to say here. We have the proportional gain, the integral time, and the derivative time for T sub I and T sub D. What happens when we put this into a digital form or write it in terms of a difference equation? Let me just give you the answer. Now U sub n is equal to, and U is the input to the into the system, and E is the error signal driving our controller. This memory, that's from our integrator. That's why we simply have this U at time n minus 1. The previous input to the system is being used to produce the next input to the system at the present time now, n. And we're going to see where all of these terms come from, but now this is just a weighted combination of the error signal now, the error signal 1 time step before, and the error signal 2 time steps before. That's the little e. So you're just weighting the error signal at different points in time and the input 1 time step before to produce the input to the system at the present time. That's a way of writing this PID controller in the discrete setting or in a difference equation form. And now I want to answer that question. How did you go, or how do we go from this capital C of S, the Laplace version of this PID controller, to its Z transform representation, the transform representation in discrete time. And how did we go from S to Z, or what did we call that earlier in the semester? Do you remember? That process of taking a filter or a controller and taking it from the analog into the digital. We had a name for that. What did we call that? Pardon? The Z is the complex frequency variable Z that's associated with the Z transform. If we want to go from the Laplace transform to the Z transform, we said that was some kind of discrete equivalent. So we're now finding the discrete equivalent, which will take us into the Z transformed version of our PID controller. Here we're just going to do some algebra with that expression in the time constant form, or in these integral and derivative time forms. First, let's factor out an S out of the denominator of all three terms, and that didn't even exist in the constant term, so we have to put an S in the numerator. We only had one S in the numerator of our derivative piece, so now we have two, and now we don't have any S associated with the direct multiplication of the integral time, or 1 over the integral time. If we cross multiply and then push the S to the left side, we end up with SU of S equaling this product of three terms that are associated with the proportional, integral, and derivative pieces of our control law. E is the Laplace transform of our error signal. U is the Laplace transform of the input. If we take that into the time domain, S times U in the frequency domain is equivalent to differentiating in the time domain. Now we're looking at the derivative of the input into our system is some linear combination of the error signal, the derivative of the error, and the second derivative of the error, based on how we know S's and S squareds, the square of S, translate into the time domain. This is just a time domain description. T is a continuous time variable in this expression. This is one way of thinking about a PID controller. It's working with the error and its derivative, essentially. Or you could think of it as, if you looked at this U, now you have E, the integral, and the derivative of E. If you just looked at U and not the derivative of U. Here's the discrete equivalence step. Now we want to approximate those derivatives with this backward difference relationship. U prime, then, to take that into the discrete time case, to obtain a discrete equivalent, we just take this difference between U now and the input U one time step before, and divide by the sample period, capital T. That shouldn't be any surprise on the left. And now we simply do that on the right, except here maybe I'm abusing notation a little bit. In the very last term, I need to essentially approximate the second derivative, and I'm going to do that in two steps. The first step, I'm saying, let me just take the derivative of E now minus the derivative of E one sample period before. And that's now I've basically approximated one of those two derivatives. And I'm going to divide that by T. Is it clear where this equation is coming from? Using the backward Euler approximation to obtain the discrete equivalent. The argument in this curly bracket, you could think of that as little n times capital T. That's really some time instant and the error signal one sample period prior to that. And we're dealing with derivatives. But this red bracket underneath that is basically saying, take what's in curly braces and now approximate those derivatives, single derivatives, so that I don't no longer have a derivative term on the right-hand side. I'm trying to get a difference equation. Meaning now, when I have the e prime of n, I've already determined how I would do e prime at the current time, and that's e of n minus 1 over t. And likewise, if I needed to find the derivative at n minus 1, I would just take e at n minus 1 minus e at n minus 2. Divide by the sample period. All of that gets divided by capital T. Now, if you replace the red bracket with what's in the blue bracket and put all of those pieces together, we actually have our difference equation for the PID controller. What's going to happen? Let's multiply every term by capital T. Then some of those t's in the denominator on the right-hand side disappear. And we introduce a t in the integral term. But everywhere else, we eliminate one of those capital T's. And do you see that u at time n minus 1, if we add it to both sides, it will appear on the right-hand side of the equality sign? And that's where that came from before in the earlier derivation, or when I just wrote it down. What's going to happen down here in the red curly braces? I have a minus e at n minus 1 minus e of n minus 1. I have two of those. And they are going to be scaled by capital T sub d. I need a bigger board. But if you can follow that along, I have k scaling everything inside square brackets. Look at what terms I have now involving little e of n. I have a k term. I have a k capital T over T sub I term. And I have, way down in the red bracket, I have e divided by t, scaled by capital K. I hope that's what I have here. I have k times basically e plus t over T sub I plus T sub d over t. That's the error signal at the present time. For whatever reason, I decided to change my indices from n's to l's. But it's the same thing. Here is that 2 that was associated with the derivative piece, and I just had a k scaling another factor of e at time L minus 1, or 1 time step before, and I just had one term associated with the error signal 2 time steps in the past. This is now the same equation that I had introduced or simply wrote down at the beginning or earlier in the lecture. Here's now how that falls out. But I'm going to get lazy and say I don't want to keep writing all of those parameters. But if you were designing a PID controller, and maybe you did it in the analog setting, you now have an integral time, a gain, and a derivative time. Once you have the sample period, now you can implement that with a difference equation, because you have all of these coefficients in this difference equation that's realizing the PID controller. What I'm going to do, though, is, I may have just storied to you. Let me see, what did I do? Okay, I'm still going to keep those. I'm going to keep the k, but now I have all of these coefficients collapsed into a new variable. Alpha 0 scales error now. Alpha 1 scales the error 1 time step into the past. And alpha sub 2 is the coefficient that scales the error 2 time steps into the past. You can now z-transform that since the above is simply a difference equation, little u of L is just capital U of Z. Every time we have a delay in our argument in the time domain, that corresponds to a z to the minus 1 factor. And now in the Z transform sense, our PID controller, realizing that those alphas contain these gain constants, it's just a linear combination of the air signal with delays and the input to the system, U. We can pull the U's to one side, the capital U's, giving us 1 minus Z to the minus 1. We can factor out the E that's common to all three terms in the P, the I, and the D piece. And now I simply have a second order polynomial in Z to the minus 1 and a first order on the left. And I can now solve that for the Z transform version of my controller, capital C of Z. That's now U over E is K alpha 0, etc. And that's maybe not how we like to see it, is it? We might actually like to see this in terms of Z's and not Z to the minus 1's. So if we simply take this, what do I want to multiply by? To convert it from Z to the minus to Z's, positive powers of Z's. I want to get rid of the highest Z to the minus, don't I? And as long as I scale by 1, I'm not going to change anything. So my 1, my magic 1, I'm going to write as Z squared over Z squared. If I push that through the numerator and the denominator, and downstairs I have Z squared minus Z, and upstairs I now have alpha sub 0 Z squared plus alpha 1 Z plus alpha sub 2. And now you can think of how you would factor that. Downstairs, what do we have? This is now just our poles that the controller introduces. And those don't have any variables associated with them. Those are fixed. And look where those poles end up. We have one pole at Z equal 1. What's that a result of? Why do we have a pole at Z equal to 1 if this is a PID controller? Where did that come from? If you were in an interview and somebody said, why in a PID controller do you have a pole at Z equal to 1? What would you say? Remember, I had that control class from THARP, from the University of Arizona, so don't expect me to answer. Don't say that. That's not a good answer, is it? Well, it's maybe a valid answer, but it would, again, mess up this logarithmic spiral in my chest, right? It might hit hard in the heart of mine. I know you don't think I have a heart, but where is that? Why do I have a pole at 1? What's that? Why is that coming into play? Where's that coming from? And now you could just answer with a P, with an I. So I could just say, give me a P, give me an I, give me a D. It's one of those three. It's a result of one of those three pieces. And what piece gives rise to a pole at Z equal to 1? And what's that equivalent to in the analog case? Remember, Z to the minus 1 is equal to S. Or actually, Z is equal to E to the ST. So what is that pole at the origin? Pole at the origin in the S domain corresponds to a pole where in the Z domain? at 1. What's a pole at the origin in the S domain correspond to? What kind of an operator? That now looks like a 1 over S in the frequency domain. What's that operation in the time domain? Integral. And now what did that correspond to in the Z domain? A pole at Z equal 1. That pole at Z equal 1, the integrator term in the PID controller gives us this Z minus 1 factor. And what's that do? That helps us with steady state accuracy. Just like it did in the analog. The more integrators you put at the origin, the better the steady state accuracy. But what are you doing to your system? You're maybe making it more difficult to stabilize and respond in the transient. It's this trade-off. Transient behavior versus steady state accuracy. Those two usually have to be weighed against each other. And what are all of the numerator pieces? Well, now you have a second order in the numerator. You can factor that. And here the betas could be complex. You might have complex zeros. They would have to be coming in complex conjugate pairs if you're allowing real coefficients, and that's what we want. You don't want to be programming your computer or your controller with imaginary coefficients or coefficients that have complex or imaginary parts. You want those coefficients to be real. You might have two real zeros or two complex conjugate zeros. This is now what the pole zero pattern of the PID controller looks like. You're forced with a pole at the origin. That's to produce basically this causality behavior. You have a pole at 1, that's the integral piece. And now beta 1 and beta sub 2 could be two real zeros. They could be zeros that are complex conjugate. Is that clear? The betas are adjustable. You should be getting comfortable looking at a Z-plane diagram and getting a feel for what might be happening. But this is what you would lay on top of an already existing system. If somebody says, oh, introduce a PID controller in the digital domain, boom, you put down those two poles, and now you get to play with where those circles are. And why do you play with those circles? Because it feels good to play with those circles. It's like you're in the sandbox and you're playing with toys. Okay, but what are those toys trying to do? What are you trying to shape? What have we spent the last 2 weeks studying? Root locus. So those zeros allow us to shape the root locus. And what's the fundamental thing you're first wanting to do? You're wanting to bring all of those branches such that at some point, simultaneously, all of those branches will be inside the stability region or inside the unit circle. That's how you're hoping to select those two zeros. So here's how we can design with a PID controller. First, we simply write down or put on our Z-plane those two poles that are fixed because we're dealing with a PID controller. One of those poles as it is at Z equal 1, one is at the origin. And here's maybe a way of keeping track of why those are there. One's helping with steady state accuracy. That's the pole at 1. That's right on the boundary of stability. And the other one is there to keep our controller causal. But then you're the designer. The designer gets to select where those, whoa. Who's sleeping now? You don't have to answer that. the designer can select two zero locations. The two poles are already forced on us. Is the wording correct? Did I have any other typos somewhere? Let's now go through an example of how we can select those two zeros. Here's a plant, g of z, 1 over z minus 3/4. What's that going to look like in terms of a block, or in terms of a root locus? There's our system. Is the system stable? If we just used a gain, can we stabilize this system with a gain controller? Don't question your judgment too much. Yes, it can be stabilized. It's already starting inside the unit circle. If you increase the gain K, you are now going to push this pole in that direction. What might be a downside to just using a gain controller for this system G of Z? Steady state accuracy. You're going to have some error between where you tell the system to go and where it actually goes. With just a gain controller, you do not have what? You do not have a pole at z equal 1 to give you zero error due to a constant input. If we now introduce a PI controller, we could simply say that K is something z minus 1. So that now, what color do I want to put my, well, since that transfer function's in green, let me do this. I put a pole there, and now let me just do this for start. Ooh, this is going to get, oh. If you're not playing along at home, you might not appreciate the real slight adjustment of erasing. I saved that horizontal line. It's not very horizontal. I didn't need to save it, I guess. But now I have two poles. I need to put a 0 in there for this PI controller. Where would you put that 0? Any ideas? Where would be a clean place to put it to make your analysis pretty trivial? 0.8. What would make it even more trivial? 0.75. If you simply put a 0 right there, now in your combination of C and G, though that stable pole 0 cancellation allows things to be pretty trivial, so that the root locus looks like it did before. It's just now you are guaranteed of what? Steady state accuracy is now there. You say go to 2, it goes to 2. You say go to 3, it goes to 3, because you have that integrator in your controller. You've now forced a pole at z equal to 1. And you can do what? You could now select z, you can select the gain, K, to put your closed loop pole wherever you want it. So K is selected or speed of response. Questions on that PI controller design? How robust is that controller? Is it clear what I mean by robust? Have I mentioned that at all? Maybe not. It's a good time to mention it. What do I mean by robust? I mean, if my plant is not quite the plant that I've modeled, is my controlled system still going to behave close to what I had thought it was going to behave like? Meaning, is my closed loop system robust against parameter changes in my system? Does it tolerate variations in my system dynamics? And what corresponds to changes in my system for this G of Z? What might I not know accurately? The pole location. I may have somehow, maybe my plant, as it's coming off the assembly line, maybe one of those is at 0.75, maybe another one's at 0.7, maybe another one's at 0.8, another one's at 0.76. Now what do I do? Well, I've already designed my controller to put a 0 at 0.75. Now your boss is going, well, then how robust is your design? Well, then you just answer your boss, right? You say, oh yeah, I had a controls class. So what do? You just, on the back of an envelope, you say, here is the Z-plane, and now maybe your boss says, wait a minute, what if your system, G, has a pole that's 0.7 and not 0.75? Well, you've placed with your PI controller, there is your PI controller. But your plant now, whoops, am I using the wrong colors for different? Yeah, let me change back. Suppose now that your plant has a pole at 0.7. Your PI controller put a pole there and a 0 right there at 0.75. Is that going to give you much different behavior than what you expected if you were right on with the 0 and the pole cancellation? What's this root locus look like? Now how many pieces of French bread do you have? 4, don't you? You only had 2 before. Is that a problem? What's the root locus of this look like? Is it hard? No, this one's easy, isn't it? Because what's your pole 0 excess? 1. How many zeros at infinity do you have? 1. Where's that asymptote for that 0 at infinity, for that branch of the root locus? It's 180 divided by 1. I can even do that division. That's at 180. This is pretty easy, isn't it? This root locus, this guy goes there, and this guy goes there. And maybe for the choice of gain K that you've picked up above, maybe now your closed loop pole is here and right there. So that closed loop pole is nearly canceled by that 0, and you really just have the dynamics of that sort of isolated triangle interior to 0.7. So this system would behave almost the same as what this one did. Your design is fairly robust, your controller design. Now you're going to ask, what? Well, wait. What if my boss tells me it's not at 0.7, but it's at 0.8? Oh, boss. What do we do? Well, you just answer that one. So suppose now I have to remember my color strategy. Here was the pole of the PI controller. We also had a 0 of that at 0.75. And now the boss says, let me trick you. Now that pole at the plant is at 0.8. Oh boy. Now what? What's this root locus look like? Can you see it? What's the pole 0 excess? 1. How many asymptotes do you have? 1. Where is it? 180. Is this going to look the same as the last root locus? Is it going to look much different when you step back and look at this from 10,000 feet? What's this root locus look like? Now you have 2 branches there, don't you, between 1 and 0.8, if that's where that blue X is. This one, I better be careful, is going right. This one is going left. They break away. This one goes to the 0, and the other one zips off here. And what happens? We have a closed loop pole there and a closed loop pole there, almost on top of that 0 again, don't we? Now, at that gain, does this look much different than any of the previous 2 in terms of dynamic behavior? Probably not. So you're okay. Even if your plant comes off the assembly line a little different than 0.75, maybe there is some modeling error between what you've modeled and what the actual system is, but if it's just a single pole system, you're probably okay with this PI controller. Is that clear? Questions on that? What if now we look at a different example? We're not going too elaborate just yet, but now what do we have? Is this system stable in the open loop? Not in the open loop. What if we close the loop? Can this system be stabilized with a gain? You'll have to crank up the gain, won't you? But there will be a range of values of gain K that will allow the closed loop pole to be inside the unit circle. You can find the minimum value of K and the maximum value of K for stability, for a gain. But again, the steady state accuracy may be unacceptable. So somebody says, let's design a PI controller for this. And what's the structure for a PI controller? If I, on the final exam, which people are telling me is 30% of your grade, they're asking, how can I catch up? You've got time. 30% of your grade is still outstanding, as are some homework and project points. But if I said, what's the structure of a PI controller? It probably won't be that easy. But if I said that on the final, what would you write down for capital C of Z? That's what you would say? Maybe, maybe not. Do you know anything about the denominator of your controller, if it's a PI controller? You have a pole at 1, don't you? You know, by definition of a PI, you've placed a pole right at 1. What else do you have? You have a 0 and a gain, don't you, that you can manipulate. You have 2 parameters that you can adjust. You have a gain and a 0. So that if that's what we have, now our plant starts there. Our PI puts that there. Where would we want to put our 0? Knowing what you know about root locus. The root locus tells you where your closed loop poles are living as you adjust the parameter K. Now you have one shaker, and really you only have one variable to place, one 0 to place on the z-plane. Where would you place that 0? I don't know. Wait until the final and I'll tell you. Well, you probably have a good idea where you want to place it already. Do you want to place it on top of the pole at 1? Probably not a good idea if you want to capture some of that 30% for your grade. You might lose 50% of your entire semester grade by canceling that pole at 1. Why? What can you not do with poles and zeros of your controllers? You can't cancel unstable poles and you can't cancel unstable zeros. Okay? With poles and zeros. You do that, sorry. No making up those points. So we can't cancel the 2 or the 1 with our 0. Where do we want to put that 0? Just in general terms. You don't have to come up with an exact answer, but now if you were doing this over a cup of coffee, where would you put that 0? Maybe between 0 and 1. If we now put that 0 between, that 0 between 0 and 1, I have too many zeros floating around. This is now at beta, isn't it? What's the root locus of this look like? Why did we spend so much time talking about root locus? So you can quickly sketch these. Do you know what this looks like? Let's say you're just going to approximate the root locus. What's happening between 1 and 2? Anything? You have now I can't even think of the animal that has pinchers, that crab, a lobster. Now you have these poles coming together, don't you? So somebody was giving me this hand signal, and I'm thinking food. I'm thinking lobster. Maybe, no, it's these 2 poles coming together, and they meet and they break away. What I was going to say is breakaway. Let's not concentrate on exactly where that is, but we know it's happening between those 2. There's 2 branches of the root locus between 1 and 2. Even though there's one line segment that the root locus lives on, there's 2 branches of the root locus. What's the pole zero excess? 1. How many zeros at infinity? 1. My finger's not changing, is it? It's stuck. What's the asymptote? 180 divided by that 1, the pole zero excess. And if we have a breakaway, let's just say it's right there. There's our radius. Is it clear how we would, or where that came from? Now, suppose we have that general structure, and now we say, well, maybe we don't want it going so big. Maybe I would like to know where to put that beta more effectively. Here I just sort of sketched it. I know I can stabilize my system with this structure, this PI control structure, based on this thinking, based on this thought process. What if we select beta? Now, this one we just sort of plopped it down. What if we select beta to produce desired root locus path? And then K is used to fix our poles, closed loop poles, somewhere on those paths or those branches. K is used to fix the dominant closed loop poles. So now it might be that somebody already has in mind where they want their closed loop poles to live. Suppose one wants these dominant poles or the closed loop poles to be at 0.9 plus and minus j 0.1 for whatever reason. What might determine those complex dominant poles? What are the parameters that might produce these z deltas? What concepts have we talked about so far this semester that might have led you to believe, or led you to this location for dominant poles? What performance specifications have we talked about? Settling time, that tells you the radius. Percent overshoot, that tells you your logarithmic spiral. Peak time, that tells you the angle. All of those might play into where that z delta came from. I'm just now giving us that value, but it could have arisen from those different kinds of design or performance specifications. What we want to ask now is, suppose somebody tells us that's where we want our closed loop poles. Is it possible to achieve those closed loop poles with a PI control structure? It doesn't look like that PI controller would do it, does it? Those branches don't look like they go close to 0.9 plus and minus j.1, do they? But is it possible to locate a beta somewhere in the z-plane that might allow the branches to actually pass through 0.9 plus and minus j.1? We are now looking at, here's something at 2, here's 1, and now what we're looking at is we may want this 0 somewhere there so that, well, who knows exactly where it's going to be. What What we do want, though, let me say, is that. Pretend that's 0.9 plus and minus j.1. That's where we want our root locus to pass through. We now want to see, is it possible to select a 0 that's located at beta to make that happen? And what do we know is true if these three poles and zeros produce a root locus branch that goes through that upper triangle? What do we know has to be true about that location of the triangle? If a branch of the root locus passes through that point, how can we verify or make that happen? What has to be true? There's two conditions that the root locus satisfies, isn't it? Always. Magnitude condition and phase condition. 1 and 2, poles at 1 and 2 are fixed. Once we've said we want triangles at 0.9 plus and minus j1, we know exactly the angles that those two contribute. We now want to know, is it possible for that 0 to contribute an angle such that all of those sum algebraically to minus 180 degrees? Meaning we have this angle, let me call that theta sub p sub 2 since it's at 2. We have this angle, it's all kind of clumped together, but then we have this angle, let's just call that theta sub z. Is it clear what my angles are? And we can now use the phase angle condition where we know that theta sub z, the sum of all of my 0 angles minus the sum of all of my pole angles must equal minus 180. Is everybody okay with that equation? So now what do we do? Well, we can actually calculate all of those angles. Theta sub z is the one we're trying to solve for. What do we hope theta sub z ends up being in terms of an angle? We hope that it ends up being something other than theta sub p1. We don't want it to the right of theta sub p1, do we? And we can kind of anticipate that's not going to be the case because of the way that the root locus is shaped, maybe. So let's compute these angles. What's theta sub p sub 2? I like to basically compute the acute angle and take that away from the larger 180. So theta sub p sub 2, I like to say, is 180 degrees minus that angle that's less than 90. And the angle that's less than 90 is the angle that has an inverse tangent. It has a vertical distance of 0.1. And what's my horizontal distance between 2 and the triangle? That triangle's at 0.9, so that's 0.1 inside 1. This is now 1.1. Are we okay with where that came from? That's now just this angle that's less than 90. It's very tiny, but that's the angle from that pole at 2 to that triangle. 180 minus that small angle. That's theta sub p sub 2. And this, if we compute this, is about 5 degrees. And that now becomes 174.8. Theta sub p sub 2. Now, theta sub z, what is theta sub p sub 1 as an angle? If we did it the same, we would say, oh, it's 180 degrees minus, how high are we going to get to that triangle from that pole at 1? What's the vertical change that we're going through? Really? 0.1, right? To go from the x at 1 to the triangle, we have to go a distance of 0.1 vertical. What's our distance horizontal? 0.1. So we have height, or vertical and horizontal, of 0.1. What kind of an angle is that? A right triangle, that's now 45 degrees, isn't it? So we subtract that from 180. Theta sub p sub 1 is 135 degrees. Is that clear? Now we have everything except theta sub z. We have theta sub z minus 135 degrees plus, let me just put this in as 180 degrees minus 5.194. It'll make my math easier. And that's equal to minus 180 degrees. So that now I can actually say that cancels that, because I'm pulling that minus sign through the parentheses, and theta sub z is now 135 degrees minus that 5.194. That's now 129.8 degrees. So the angle of the zero of my PI controller needs to contribute about 130 degrees. Where does that put the zero? If I'm sketching geometrically this picture, and here's 1 and here's 0.9, and my triangle is right there, that's 0.1 up if my horizontal is 0.1 there. Where is my zero? If the angle of that zero is 130 degrees, is it to the left of the triangle or to the right of the triangle? It's to the right, isn't it? My zero now of this PI controller is now somewhere there, isn't it? Meaning this angle is the 128 or 129.8. Like I said, like to work with these angles that are less than 90. Let me call that theta sub z bar. And I might be interested, I am interested in this distance from 0.9 over to the 0, and let me call that distance x bar. Because this, I've got too many things, I should have made this even bigger. This is located at beta, that 0. So that now 0.9 plus x bar is equal to beta. I'm trying to find beta. And given what I now know, I can actually solve for x bar from trigonometry with right triangles. Is that clear? I know the vertical distance, that's 0.1. I don't know x bar, but I know theta sub z bar. That's the supplementary angle of 130 degrees. So that now theta sub z bar the way that I defined it was 180 degrees minus theta sub z, so this is now 50.194 degrees. The tangent of that angle is equal to the vertical height over the ratio of the vertical distance, 0.1, to the horizontal distance, x bar. I can now solve that for x bar. That gives me 0.0833, so that now in this picture, here's 0.9, here's 1, here's my triangle, and now I know this x bar distance will give me my beta. So that now beta is 0.9 plus x bar, which is 0.9833. Now I have found one of my two parameters in my PI controller. I found the zero, I found the beta. I was able to find that based on the phase angle condition. That forced the root locus to go through that triangle. Now I need to find k. How do I find k? I know this is going to be true. I now know that I have that, and this is at 0.98. It's very close, isn't it, to that zero, or to the pole. I now know that this root locus does something like that. But now what I want to do is find the gain k to get me to that green triangle. And I can use the magnitude condition, my other condition on the root locus, to find that k. Because I know that the product of my controller times the plant has a magnitude of 1. And if I solve that for k, I have to plug in a specific value for z. What z do I plug in? We've forgotten? 0.9 plus J1, that's where we wanted to be on that root locus. So that's where we evaluate this gain. This is now at 0.9 plus J 0.1. You could do it at 0.9 minus J 0.1. It'll give you exactly the same gain. This ends up being 1.2002. Now we have our controller. now have our PI controller. And what's that going to give for us? Apparently, it's giving us the transient behavior that we want. We said we wanted 0.9 plus and minus j.1, and what do we know about the steady state accuracy? It's good due to constants, isn't it? Because we have that pole at z equal 1. We have this pure integrator in our controlled system. What if we weren't happy with the response that this controller is producing? Are we out of options? What did we do with this C of Z, or what kind of a controller were we using with this C of Z? PI. We didn't use all of our alphabets. We have a wheel of fortune we can spin and ask for a D, right? Hopefully it's on the board. Has that ever been a clue on Wheel of Fortune, PID? I don't want Wheel of Fortune. Maybe they need to have a clue, proportional integral derivative. Then you could really get a lot of money on that wheel, couldn't you? Proportional is a pretty good long word. What would be the letter you would select if you landed on $1,000? Proportional integral derivative. And you don't want to buy a vowel. I don't know, for some reason N seems to be might have quite a few. Anyway, where was I? Let's ask Vanna for a D. So let's try a PID controller. What's that give for us? What's the structure? Now on the final, I now say, what's the structure? What's the generic structure of a PID controller? What are you going to write down? If you wanted partial credit, you could say, oh, I've already bought a vowel. I have the I. You know that gives you a pole at z equal to 1. That's the integrator. That gives you your steady state accuracy. That's what we're happy with that PI. Maybe we weren't so happy with the transient behavior. We've now introduced the D. That now forces this. What else does that give us? How many parameters do we have to play with now in a PID controller? How many did we have to play with in the PI controller? 2. Gain and 0 location. With the PID, what do we have now? We have the gain and 2 zeros. Now we can do K, Z minus beta 1, Z minus beta sub 2. So that now, if we had a PID controller, we've bought a D, or no, we didn't buy a D, we just requested, didn't we? Have to buy the vowels, and we'd already bought the vowel. We already had the I. Sorry. Now what does this look like? We started our system there, didn't we? Then we introduced the PID controller. Now what do we do? We're locked in. I don't know about you, but did anybody bring a sandwich? Oh, this is being recorded, isn't it? Oh, well. I thought I heard the door. I assumed that was the lock. We must be about out of time. Vanna must be finishing the show. So what do we do? Where do we put those zeros? Do you see what might happen if we locate our zeros? Where would we put our zeros? Where would be a location for the zeros that we've already done? We could cancel that pole at the origin and put the 0 back at 0.9833, and then we would have a PI controller, wouldn't we? Why'd we get that D from Vanna? So we could vary a little bit from that, couldn't we? We know that that works. Maybe if we slide that 0 a little bit off of this pole, maybe if we put this here and that there, now what's the root locus look like? I'm getting a little nervous with this. Now do we have this? What else do we have? This and that. These are at 1 and 2, aren't they? What's going to happen? This guy's going to march off to minus infinity. These two and we'll crank up the gain to what? Make sure that those two branches get inside the unit circle before that third one goes off to minus infinity. That would be our issue that we would have to be concerned with adjusting the gain K. I'll stop at that point, but I hope that it's starting to make some sense in terms of how do you place poles and zeros in the PID controller.